Welcome to the Explainer. If you're verifying modern hardware designs, you know configuration and status registers are literally everywhere. Today, we're demystifying the UVM Register Abstraction Layer, or RAL. We're going to dive deep into how you can stop manually grinding through register testing and just let the test bench do the heavy lifting for you.
Think about the sheer scale of the problem we're facing. Picture a modern system on chip containing, over 100 unique IP blocks. Each one of those blocks might have dozens or even hundreds of configuration registers. Now, verifying that massive design without RAL, you're talking about writing thousands upon thousands of lines of incredibly fragile, repetitive bus protocol code just to flip a few bits. It's a nightmare. But with RAL, we can completely automate and abstract that entire process away.
So, here's our roadmap for today. 1. Why use UVM RAL? 2. Register model hierarchy. 3. Adapters and predictors. 4. Front door versus backdoor access. 5. Mirroring and state tracking. And finally, 6. Automated register testing. Let's get right into it.
Section 1. Why use UVM RAL? The need for abstraction.
The difference here is, well, it's basically night and day. Without RAL, if a base address changes, which happens all the time, right? You are stuck hunting down hard-coded addresses scattered all throughout your sequences. But with RAL's object-oriented model, you just make a high-level call, something like uart_control_reg.write, and boom, the abstraction layer just figures out the physical address and the bus protocol for you. It's really that simple.
Section 2. Register model hierarchy. Mapping to design.
Now, when we build a register model, it forms a hierarchy that maps perfectly to your physical layout. At the very top, you've got the overarching blocks, and those break down into individual registers, and then finally down to the specific fields. It acts as a flawless, logical mirror of the actual physical hardware.
Let's break down those specific components. You have the UVM Reg block, which is your top-level container mapping to a specific IP, like a UART or a MAC. Inside that, you've got instances of UVM Reg, representing the actual 32-bit or 64-bit registers. Down at the finest level of granularity, there's the UVM Reg field, which represents the specific bit slices, like an enable bit or a status flag. Oh, and there's also UVM Mem for abstracting memory read and write operations. Because there are just so many tiny details involved here, these classes are almost always specialized by a correct by construction model generation. You don't definitely write them by hand. You just feed your hardware spec into a tool, and it generates this whole class hierarchy for you.
Section 3. Adapters and predictors. Bridging the gap.
Think of the adapter as your test bench's translator. It takes a generic register address or data read and converts it into a specific bus transaction, like APB or ACI, whatever standard protocols your chip uses. So when you call a write on your register model, it creates a generic operation. It hands that over to the adapter, and the adapter translates it into the exact sequence item your specific bus agent needs to actually wiggle the pins on the physical interface.
When you dive into the actual APB reg-to-bus adapter code, you can really see how straightforward translating a generic request is. We just check the generic read-write kind. Is it a UVM read? And then we simply map that directly to the specific APB read operation enum. We do the exact same thing for the address and the data. And keep in mind, the adapter also has a bus-to-reg method that does the exact opposite, pulling physical responses back up into generic data the model can actually digest.
Okay, so that brings us to the predictor. The predictor basically works in reverse of the adapter. It takes observed bus transactions from the bus monitor, looks up the corresponding register, and updates the model. Now, why do we even need this? Well, because your test bench absolutely has to track the internal state of the hardware. So the predictor sits there passively watching all the traffic on the bus, uses that bus-to-reg method to decode it, finds the register in the address map, and updates your test bench's local copy.
Section 4. Front door versus backdoor access. Access mechanisms.
Choosing your entryway is absolutely critical here. The front door is kind of like walking right up the driveway. It consumes simulation time, toggles the clocks, and verifies the actual physical pathway. The back door, on the other hand, is like sneaking in via a secret zero-time tunnel. It hooks directly into the simulator's memory using a hierarchical string path, something like top.uart.control_reg, letting you read or write the register instantly without burning any clock cycles.
When we're using that backdoor access, we rely on two very specific methods. Peak grabs the value instantly without causing any physical side effects, so it won't accidentally clear a read-to-clear register.
and poke forcefully deposits a specific value right into the register. This is incredibly useful, honestly a real game changer, for setting up complex hardware states in zero simulation time before you kick off a specific test scenario.
Section 5. Mirroring and State Tracking. Reflecting state.
So, here's the million-dollar question. How do we ensure our abstract register model perfectly matches the actual physical state of the design? This is the core challenge of register verification. If your test bench's reflection of reality is out of sync, your tests are going to fail, or, even worse, they'll pass incorrectly. UVM RAL solves this by maintaining a mirrored value for every single register. It's essentially the test bench's belief of what the hardware currently holds.
But keeping that mirror perfectly accurate means choosing the right prediction strategy. Here's the trade-off. You've got auto-predict mode, which is definitely simpler. The mirror updates the moment your sequence issues a write. But wait, what if a different bus master on the chip writes to that exact same register? Suddenly, your model is totally blind. That's why explicit prediction is so much more robust. By turning autopredict off and relying on that explicit UVM reg predictor connected to the bus monitor, you capture absolutely everything happening on the physical bus, which guarantees your mirror is always completely accurate.
Section 6. Automated register testing. Effortless verification.
Now, the real magic happens with just one single method called doTestAll. Executing that one line triggers built-in UVM register tests that verify reset values, access policies, and reserve bits across your entire design. I mean, think about that. You don't have to write a custom test to check if a read-only register accidentally accepts a write. You don't need a sequence to ensure every register correctly resets. UVM provides these predefined sequences that sweep through your entire auto-generated model and thoroughly stress test the hardware completely automatically.
It is absolutely time to stop manually writing protocol code and start leveraging the full power of RAL. Whether you're utilizing front door accesses, maintaining perfect state tracking, or running massive automated test sweeps, RAL really is the engine for scalable hardware verification. Thanks for joining me on this explainer. The only question left is, are you ready to let automation actually do the heavy lifting in your next test?